Good morning. Let's see. Today is Tuesday, the 24th of July, 2018. My name's Jeff, and this is the nybbles.io daily programming stream. I write code every day, 5 a.m. to 10 a.m. typically, and I stream those sessions Monday through Saturday here on Twitch. My Twitch channel is twitch.tv/nybbles.io. That's nybbles.io. I also have a YouTube channel with the same name. My Twitch account is nybbles_io. And I occasionally post some interesting stuff on there. So today we're going to work on the compiler some more. But first, I had an anonymous request to kind of do what I did with the money example. Someone said to me, here's a problem. And I've actually seen this problem before. Interestingly enough, I have a game that I wrote. The code's on my GitHub profile that uses this same exact problem for gameplay. So what's the problem? I think it goes by a bunch of different names. Longest contiguous segment, largest connected section. But basically the gist is, and again, this is something people are being asked in interviews. So we're going to have a matrix or grid, however you want to think of it. Let's just make it really simple. 2, 3, 4, 5, 6, 7, 8. So actually, so 8 by 8. And you're going to have sections that are, let's say these are color numbers, or it doesn't really matter, right? It could be anything. So what you need to do in this problem is, what's the longest connected segment? Well, it's the 3s. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I think the 2s are 1, 2, 3, 4, 5, 6, 7, right? So it'd be the 3s at 10, the 2s at 7, and the 1s at 3, 4, 5. And then 0. We'll say 0 doesn't count in this example, although it depends, right? So you have to be careful. You have to ask a lot of questions. So this is the basic idea behind the problem. Here are the kinds of questions I would ask if I was given this problem up front. First, how big can the matrix be? You need to know that. They may tell you, it can only ever be, 256 wide by 256 tall, or that's another question you need to ask. Are the width and the height the same, or can they be different? In other words, is it a regularly sized matrix, or is it an irregular matrix? So you need to know how big it can be. You need to know if the width and the height are always the same. You need to understand the values in the cells, right? What is a cell? Are there special meanings of values in the cell? In other words, in this case, if I say, okay, these are colors and 0 is ignored, right? We don't care about zeros, so we don't count them, okay? Or if we count them, they don't count in terms of the largest. But you need to ask. You need to know what the parameters are for what's in the cell. Now, there's a couple reasons for that. Also, you kind of need to know what data type you might want to use to store this. So if they're colors, do they need to be, how many colors are possible? If they're some other thing, how many possibilities are there? And that might seem like a trivial question to ask, but it's important because you need to know if you're going to keep track of these, you're probably going to use a dictionary of some kind of map. What is that thing that you're counting? How many possible entries in this thing this set of things you're counting, how many possibilities are there, right? If it's colors, and there can only be 255 colors, or 256 colors. Again, if we're excluding something, right? Say we're excluding 0, so 255. Okay, that's a byte. So then that means our map or whatever we're using to collect the counts of these can only ever be 255 entries in size. But if they tell you, no, it's got to be a 32-bit integer, or then obviously the space of what you're potentially storing is quite large. So now, the very first thing that you might be tempted to do is say, well, I'll just use an array. And for whiteboarding stuff, you do tend to want to go as simple as you possibly can. But arrays are, can be a little challenging. What I would do, because I kind of view this sort of problem as a subset of graphs, is I would create, the very first thing I would create is a, let's call this a color node T, okay? And we'll say that each value, there can only be 15 colors, which we can fit that in a byte, super easy. But then we know that there's going to be something that's up, down, left, right. Now, you're going to have to justify this approach as you're doing this, because depending on CPU, but let's assume a 64-bit platform, I just burned, 33 bytes and possibly some alignment for that structure. Now, here's the thing. I mean, again, that's not, in modern systems, that's not horrible at all, really. So they might say, well, why wouldn't you just use an array? Well, here's the answer I would give there. Yeah, I could probably solve the problem with an array in the simplest case, except I have to then worry heavily about bounds checking. I have to, in the algorithm itself, right? So there's a difference between code that loads things or sets things up from a performance characteristic and then the actual code that's solving the problem, right? And oftentimes a lot of these questions they're looking for you to talk about engineering trade-offs. They're looking for you to talk about space-time trade-offs, right? Well, if I eat a little bit more memory, then over here, I get this kind of performance benefit, right? And again, it helps to be able to do simple estimated spitballing, right? So if we say that, rounding up, this is 34 bytes. Okay, well that's, about the size of a GUID, okay, or a UUID. So you could basically say, well, people use UUIDs all the time. Yeah, they're a little bit heavy, but it's not, it's not that big. And, and you could ask questions. Okay, well, how big is the machine? How much memory do I have? And then you could easily, they're going to probably tell you, oh, well, you'll have 4 gigs of memory, or you'll have 1 gig of memory. Well, you can easily then start breaking this down and saying, okay, well, I could store a structure that would be, 100,000 wide by 100,000 tall or whatever. And if I've had this happen to me personally, not with this specific question, but I've had interviewers then tell me, oh, well, it has to be infinitely large or it has to support infinite sizing. And I tend to push back on that stuff a little bit. And you want to do it tactfully. But the reality is there is no engineering problem that, I mean, someone doesn't come to you and say, build infinity. You can't do that. There have to be some limits. The limits might be very large, but there need to be some reasonable, concrete limits around what you're building. And I would say if they persist and they're like, oh, no, it has to be unlimited or it has to scale to, you know, arbitrarily large amounts of memory or whatever, you probably don't want to work with them. That would be my thing. But coming back to the problem, what's nice about this structure? Well, what's nice about this structure is we have pointers, because how do we solve this problem? The way we solve this problem is procedurally is pretty simple. We have some data structure that tells us if we visited a particular cell in the grid, okay? And that's just on off. Have we been there? Yes or no? That's one thing. When we visit a particular cell in the grid, we want to walk our neighbors, okay? So the way we would do that is we would have a recursive function. Maybe we'll just call it walk node or walk color node, and it'll take in a color node T pointer. And then we have now pointers up, down, left, right. And if these are null, we don't go there. That's our bounds checking. We don't have to worry about, oh, you know, am I at this location in the array and can I subtract and will I go out of bounds? We don't have to worry about that, right? These things will get wired up and we'll know exactly where to go based on that information, okay? So we're going to start on a cell. We're going to try to go up. We're going to try to go down. So if we go down, there's something here. And one of the very first things we do inside of our walk node is we ask, have we been here before? And if we have been, if we visited it, we bail, right? So the same algorithm would apply. We'd go up, but when we go up, that's going to check that cell and it's going to bail on that. Now, you can do the check from a recursive perspective. You can do the check inside of the node walker. So you recurse into it, you check, and then you bail. But there's a cost for that. So this is another area where you're most likely going to get questions. They're going to say, you know, well, should you check before you make the call or should you check after you make the call? And you need to be able to describe what the trade-offs are on that, right? So the trade-off of having the check be part of the recursion is it's part of the recursion, meaning that you have to, you know, you're paying the price of creating another stack frame, calling that function recursively, then checking and then bailing. So you're paying a price to determine that, oh, I don't want to go there. And in this particular problem, the longer it runs, the more heavily you're hitting that case. So the other thing you can do is instead of the check being based on the node that's passed in, you can check before you call, right? So you can basically say, okay, I have an up, I want to go up, but should I? So before you even make the call, you check your visited mark for that node, and if you've been there, then there's no reason to make the call. Now you're saving a level of recursion. So you only recurse if you haven't visited that particular node and there's a node there to visit. So on the edges, obviously these have no ups. On the right, these have no rights. On the left, these have no lefts. On the bottom, these have no downs. And it's a trivial check, right? We're not doing goofy indexing, which is hard to do on a whiteboard. So that's the other thing too, is there's nothing wrong, in my opinion, with optimizing your solutions to the fact that you're doing this on a whiteboard or you're doing this under a stressful situation. Make the problem easy on yourself, right? There's no reason to make it more complicated than it needs to be. So this represents one cell or node in this structure. And we have pointers that we set up that connect us to our neighbors. So we've already talked about, this, yes, is a little bit more heavyweight than, using an array. But here's the other thing you're going to say too. You're going to say, okay, well, this is a really simple example, right? You're just having me check a color number or something and count those up. But we're probably going to have a bigger or more complex payload in a real world example. So, having a structure already and having these combined together, makes sense. So that's the answer that I would go with. Okay, so now, how do we build this? And what do we build it into? So we can, this is C++, so I would certainly just do the simplest thing that you can. I'd use, I'd call this color node list T. Hey, 1, 2, 3 film. So I just use a standard vector of color node T's. If you're going to, I'm writing this in C++. Typically what I do, and then this depends on environment, right? And you have to practice this on a whiteboard. Hopefully they're not making you do this on a whiteboard, but if they are, look at the whiteboard setup. Are there 2 whiteboards in the room? Is there one? If there's one, is it divided into sections? What I would do, and again, this is a negotiation during the interview. You have to speak up. You have to sort of advocate for yourself as you're going through the process. So as you're going through the process, what I would say is, okay, I'm going to write my solution in C++. Is that okay? They're going to say yes or no or whatever, or shrug their shoulders, or whatever they do. And then you're going to get some tacit approval, or they're going to outright tell you no, don't use C++. Or maybe an interviewer might say, well, are you really sure? In my case, I'm like, yeah, I'm okay with it. But you might get interviewers like, well, would you rather use Java or whatever. And that's, I got a request, an anonymous request to talk about a problem that somebody had in an interview. So that's what I'm doing here real quick before we get started in compiler land. So, and I've seen this problem before, so I thought, okay, I'll go through this. But if the whiteboard's segmented, right, or sectioned, what I would say is, okay, this is C++ or this is C. I need to do includes and some other stuff that's at the top, and then I'm going to have my actual functions. Can we agree that this part of the whiteboard is all the code before main, this is main, that sort of thing, right? So that you're not having to erase and you're not having to find space on the whiteboard. You just, you have these different lists that are all considered the source code, but you've kind of negotiated up front that one part of the board is where all your definitions and stuff are going to go, and then the middle maybe is where all your code's going to go. And so you want to negotiate that, but make sure if you are doing C or C++ in an interview, And this is also true of C Sharp, Java, anything where you have to include something or import something or use something, make sure you do it. I mean, it's one thing if you botch the name of the header file, okay, whatever. I mean, unless they're total dicks, they're not going to hold it against you. But the fact that you remembered, oh, I have to include this, or I have to import this namespace, or I have to load this module, right? Those are small little brownie points that add up. Okay, so we have a type def for a list of nodes, and we want to create a function that will read these in, okay? So so what I'm going to do is I am going to, and again, I think this is okay in an interview. I am going to assume we're going to load this from some input source, but I'm not going to spend the time to write a file reader and a parser, and because that's just extra code. So instead, we're going to pass in a string, an input string. We're going to read it as if, you know, this was coming from a file or whatever. So yeah, we'll just call it test grid, and again, I'm going to do this really simple. Let's, in fact, just cheat, because I already put that there. Might as well, right? Now, there's a couple different ways that you can do this. I suggest being over prescriptive with solutions like this, meaning I would pass in the width and the height so that you're not trying to infer it, because that just makes dealing with the input harder, right? So by having this information here, and actually I probably would change the order, so height, width. We don't have to have line feeds in here. They're just a string of numbers. Now I've formatted them in the source code so it's readable as a grid, but it doesn't have to be that way in the file. So in the file, you would theoretically have a height and a width that you would read, or that would get passed in the command line, however that works, right? But, and again, I think those are things in problems like this. Again, you can ask these questions. How important is the input structure? Do you have a specific format in mind? Can I just do something that fits this situation? Typically, they're just going to say, do whatever works the best for you, right? They're not going to have really hard requirements there. And if somebody's a real bugaboo about, this part of it, then again, like, I kind of treat that as a red flag. But we know now that we can make a color node list T, and actually, don't want to do it that way. So that's the other thing too. I would here, let's pass the reference in. So if load color grid, and the width is, or height's 8, width's 8, and the input is test grid, and we're going to pass in a reference to this. Now, what I would say here is, I would say, okay, I recognize that I'm not going to be handling a lot of air conditions in this example. However, I'm planning for it. I'm planning for the reality that something could go wrong with this, and I'm going to have to handle that condition. I think that's sufficient for problems like this. You need to just acknowledge that you're designing around error states and that you're considering them, especially with things around input. But in general, you want to try to cover those things as you're building them. Again, unless they're really not nice, you know, they're not going to hold the fact that you aren't doing a full-blown file handling and covering every possible edge case and signal and every, you know, they're going to let that go, right? And I would say again, if they don't, then that's a sign, okay? That's not good. So the easiest thing to do here is we want to reserve height times width. Okay, so this is a big one. Again, if there's a theme in any of these problems that they give people, whether you're doing this in C or C++, or you're doing this in Java or Python or anything, right? And this is why it's kind of silly, because if you're doing this in one of these garbage collected languages, they still expect you to understand what the cost of doing it is, right? So even though it's higher level and, you know, the framework's taking care of memory for you, they still want you to understand how much memory is involved, right? So, and obviously that can be pretty tricky, because if you don't understand the internals of whatever language platform you're writing on, you may not know what the cost is in totality of something. Python object headers are actually quite large. So there can be a lot of cost there, even for the most trivial things. But what I would say in general is you want to acknowledge the fact that you need to have a certain amount of memory, and that you might be able to help the language not waste time and not waste space by giving it hints. So as an example, in C++, if I create a standard vector, it's just a shell, right? There's nothing other than the size of the object structure itself. There's not much cost here. But I know I'm going to start filling the list with a bunch of stuff. So, and especially in this case, I'm going to be filling it with a bunch of structs that have a certain size. If I don't tell the list, hey, here's how many of these I'm going to have, it's going to reallocate. It's because by default, you know, standard vector allocates a teeny tiny amount of memory for the list itself. And that's expensive, right? And this is also true in Java and in C#. When you create like lists of things, dictionaries of things, you can pass in initial capacities. And this will tell the runtimes, hey, pre-allocate or make space for this number of things. These are kinds of questions, these are little things that people will throw at you in an interview. And it will throw you off guard if you're not prepared for it. But it goes without saying that if they're giving you a problem like this, they're driving to see if you understand real engineering trade-offs, right? Everything lives in memory. Some stuff's on the stack, some stuff's in RAM or in the heap. Some stuff is really costly to allocate, some stuff isn't. They're looking for you to be able to at least approximately answer about what those things are and what those trade-offs are. So especially in C or C++, you want to tell your list ahead of time, hey, this is how many of these things I'm going to be putting inside. And so now in this case, we have to populate these as we go along. So the easiest way I can think of off the top of my head to do that is to have a double loop here. And now, again, we don't technically need that because this is just a contiguous stream of characters. We could just loop through the characters, convert them into integers, then do stuff. But I'm trying to avoid, at every turn I can here, I'm trying to avoid doing weird computed indices into arrays and things, because that's where you can get messed up very quickly. Now we do need to track, in addition to where we're at in the grid, we need to track the index into the string, okay? So, so here we just need the number, right? So I would just use A to I here. I wouldn't get too complicated or fancy with streams or anything. Again, obviously different languages, different solutions slightly. In Java and C#, this is pretty simple. Their mechanisms for doing this are not difficult at all. And this needs a cast. Obviously, you wouldn't have that probably on a whiteboard. So just kind of remember, as best you can, again, you're going to make mistakes on a whiteboard. It is a given. You want your code to be as close to compilable as possible, but it's been my experience that no matter how diligent you are going to miss some small things on a whiteboard. And of course, you will notice them immediately after the interview concludes. Okay, so we need a color node T, and here we have the color. We can actually just do this assignment right in line. Now, up, down, left, right. How will we do these? Okay, so let's just, actually, let's do this. Now, if you are writing code on a machine, right, ask if you can use the tools that you're comfortable with. Hey, I like to use C-Line. Can I download that real quick? I have a license for it. And even if you don't have a license, it's free to test for 30 days, right? Or if you like Vim and they, can I set that up real quick? Or now again, that it behooves you to have your own configurations and things that are easily accessible. Like, hey, I have my .vim folder up on GitHub, or I have my Emacs configuration. Can I clone that down real quick? And ask. They may tell you no, but all you can do is try. So for up, we're going to say if y is greater than 0. For down, we're going to say if y is less than height minus 1. For left, we're going to say x is greater than 0. And for right, if x is less than width minus 1. Now, in other languages, okay, like C# or Java, you may have to write this slightly differently, okay? In C or C++, I can cheat because this is a vector of actual color node T structs. And I've reserved that memory key here. I've reserved it. So there's already a block of data. Now it doesn't, pointers don't care what's there, right? You're just telling it point at this location in memory. So even though I haven't built a particular node yet, necessarily, like for example, I won't have built the right node yet. but that's okay. I can build a pointer for it here now, and by the time this loop is complete, that will point at legitimate data. Now again, in other languages, you might have to do this slightly differently. You might want to first fill the array, right? So yeah, one way you could do this, if we didn't do it the way I'm going to do it, is you could loop through the characters real quick, convert them into colored numbers, populate the nodes in the list, right? So that would just be a simple loop to populate all the data. Now it's all there. Then you could just loop over the list, again, using this kind of a structure. Now everything is there. All the data is populated. Then you could set your up, down, left, rights, because now there's valid references for everything. Again, like if you were doing this in C# or Java, that would probably be, or even like Ruby or Python or something, that would be a better way, because then you have references to actually point at. But again, in C++ land, I can cheat. So this is pretty easy. This is just the address of our list. Some of them do. Yeah, some of them have broadcast capabilities. But again, there's limits to that, right? Like how complex the fill constructors are. So for up, so the way we would compute an index here is y minus 1 times width plus x, okay? And so we're getting the address of the color node T that lives at that location. Now again, these are not valid until the this loop is complete. These loops are complete. But that's okay. So the left is, we don't alter y. I gotta make sure I get my parentheses right here. So actually, I would put the extra parentheses here, even though the compiler is going to do the right thing. All right, and then this one is x plus 1, right? Okay, so this is going to populate our list, and we're going to have up, down, left, rights, and away we go. Now, let's talk briefly about this identity or this visited thing that we're going to need. So there are two ways that you could address the identity of the node. One is implicitly by location. Obviously, I've kind of already sort of shied away from that on a lot of this because, again, implicit stuff can be cool and it can save some things. And certainly you would want to be prepared to discuss like why you wouldn't want to use the implicit location as its identity, right? Because that is, you could argue in this context, that is the identity. So again, let me, I guess, clarify what I mean there. This has a Y position and an X position inside of the grid, right? So if we assume that Y starts at the top and goes down and X goes from left to right, this has a unique Y and X combination. And then we can find the index of that thing in any list by taking Y times the width of the grid plus X, and we can index into that. So that is certainly a way of uniquely identifying it. Another way is we could just put an ID on here. And honestly, that's probably, and we'll just make it a size T. Why not? That's probably what I would do. So why do it that way? Well, when we do the identity checking, then we don't have to compute things again, right? Because again, a lot of these tests, a lot of these questions, they're looking to see if you are, wasteful is not the right term, you're cognizant of costs. Are you aware of the fact that you have to recompute this over and over again if you use the location? Yes, you could create a function for that. You could create a macro. There's all sorts of ways you could solve that problem, but you're still computing things. As where, well, why compute it if, because all we need is a unique index. We just need a unique number. So if we have a node, we have a pointer to a node, then all we need is a way of using that to map identity, okay? Why recompute anything if you don't have to? Now, of course, everything I'm saying here is just based on my experience with these things. You may find that you hit an interview and an interviewer that they don't give a shit, right? Like that's not important to them. They'd be totally fine if you recomputed this stuff. There is no one right answer. So I'm trying to give some general hints around things that come up. So, okay. Now, identity, visited. How are we going to do that? All right. So, visited, well, let's do color node visited T is standard Bitset. And let's see, I always forget. You see right here, I'm breaking a rule because, okay, let's do, so there is this really beautiful structure. The problem is you have to tell it what size you want, which we know obviously in a whiteboard, you're either going to be erasing if you're doing this. And that's why whiteboarding is so difficult. Like I will flat out say, doing this stuff on a whiteboard is painful. It was painful. Oops. And you have to spell right. That'll work. We can pass that in. So internally, what is a bitset? A bitset is they will pre-allocate to the next highest power of 2 the number of underlying data types necessary to store this many bits, right? So actually in this case, this is just one 64-bit value. But if you had a grid, right, that was massive, then this would be a very efficient collapsed identity set for that, whatever it is you're using it for. Now, this is not the only way you could do it. You could use a set. You could use, although for a set, depending on the language, you may need a custom structure type so that you can have it have its own equality. You could certainly use a map. And really, in general, they are looking for you to use a map of some kind for this. So that's something to keep in mind. And they're also looking for you to be able to explain why you would use a map and not an array or something like that. All right. But we also yeah. Yeah, that one is a little. See, the thing I don't like about this is a beautiful structure, except they made this size. How can I do? Do it that way? No. Oh, what am I doing? No. It needs to type. Let's not use the Bitset. I'd like to, but it doesn't fit the problem very well. So instead, what can we do? I don't want to build something that's too specific here. So let's do this. Actually, no. I just had a thought. Because I built this structure, right? You can just do that. Nice. Okay, so we're just going to call walk color node, and we're going to pass the address of the first node. And now we need to accumulate. Part of the idea here is to count contiguous sections, right? So, or to count up the the occurrence of one particular number. So there's a couple different ways the problem can be phrased. I believe the person that asked me about theirs, it was count the total number of connected. So it's 2 has a 2 next to it, so that goes up by 1. This 2 has a 2 next to it, so that goes up by 1. This 2 has a 2 below it, this 2 has a 2 below it, so on and so forth. So those all add to the count of 2s because they're connected. But if there was a 0 here, this would be 3, this would be 3, this column here, because these are not connected, right? So that's part of the reason why we have to walk this. If all we had to do is just count the occurrences of particular numbers, we wouldn't have to do the walking. So what we need is a map. And we'll just call it color node result T. And I'm going to use an ordered map because I think it'll just be easier, and the performance penalty between an ordered map and an unordered map is not really that high. So this is going to be the color number and a count. Now, again, in an interview type setup here, I would be tempted to cheat slightly. And when I say cheat, I just mean set things up so that I know things are going to be the way they should be without having to have a lot of code strewn throughout the solution. So as an example, early on, I said, okay, there's only going to be, 0 through 9 colors. I said 15, but screw it, we won't even worry about hex. We'll just 0 through 9 colors. And so then I can write a loop here. And I can just insert into a map. So color node result T, results. Zero. Right. And then in our walk color node, we're going to pass in a color node T pointer, and we're going to pass in a color node result T reference so that we can keep track of results as we're walking. So here, just pass results. So what this is doing is this is making it to where when we end up in here, I don't have to worry about the dictionary, right? It's like I can look up that, I can use the subscript operator on the map and I can get to that color number and there's a number there and I can update it. It's much, much easier to do it that way than otherwise. Because otherwise we'd have to either write a helper function or we would have to have code in here to check, is that already tracked? No, it's not, so on and so forth. Okay, so the walk is we're going to have if node up is not null, sorry, and node up visited, if it's not been visited, down, left, right. So, and actually I'll go clockwise. So up, right, down, left. Now, let's change the signature there. Because for counting purposes, it's going to be super easy. Well, so actually, what do you think about that? It might be easier just to return. Yeah. So it goes without saying, you definitely want to check the node that comes in for null and if it is, you want to bail. Okay, so if we have an up, then we're going to walk node up, passing this, and we can just duplicate this. If you're getting the feeling that doing this on a whiteboard would be like very difficult, then you're getting the right feeling. This is why people bomb. I mean, this is not an exceptionally difficult problem, but I've been working on this now for an hour, and I'm using an IDE, and I'm writing code, and I can actually run it. I have IntelliSense, and I've done this problem before. Now, granted, I'm explaining myself a lot, but really, honestly, me explaining this to you would be similar to me explaining this to an interview. I mean, at this point, I definitely would have failed in the sense that the interview probably would have only been, if I were lucky, it would have been an hour. But it probably would have been like 45 minutes or 40 minutes. It's very, very difficult to do this, to do problems like this in the time, allotted. So if there's one thing I will try to convey on this, it's don't feel bad. Because, yeah, you shouldn't. So, all right, if there's an up, we're going to walk the up. We're going to get the color for up. If the color of the node that we're on, right? So here we're on 0. And to our right is a 0, to our bottom is a 0. So, and then of course this is going to recurse all the way down. It's going to cause us to spider out and get a new node, okay? So if I'm on this node, what we're looking for is, are one of the nodes that I visited, does the color number match myself, right? And as long as that holds true, right, then that adds to our count. So if up color is equal to node color, then results sub node color plus equal 1. And then we want to loop over the key value pairs in our results map. And we want to output the key and the count. And then Okay. Now, of course, on a whiteboard, your chances of being able to run this are pretty low. That's interesting. What is it complaining about? Yeah, so obviously on a whiteboard, you're not going to be able to run it. So you aren't going to catch things like that. That's interesting. And obviously, the better memory you have, this is one of those, I always have to look shit up. These small details, like how do I do fixed width columns with standard output streams, you know? Oh, and see, and this is another one where this is a uint 8t. You have to be careful because what it's doing is it thinks it's a character, but it's not, it's a number. So you have to be really careful with that too. And then my size was off by 1. All right, so we're not getting any counts though. But I think I know why. Oops, if I hit the right keys. Yeah. Oh, see, these simple little things, right, where I didn't put it in the list. Duh. Like I said, man, this is like doing this on the whiteboard is very difficult, very, very difficult. Okay, so we're getting 2 for 0, but we're not recursing anywhere else, which of course isn't right. Oh, and that's because, see? Now see, on a whiteboard, you probably wouldn't make this kind of mistake because obviously you have to rewrite it. But if you are doing this like in an editor or a shared session or something, like a pair programming session, so I cut and pasted a bunch of stuff, and I didn't change things. Yeah, see, this now is recursing. But we blew up somewhere. So this is up, down, left, but now right. Up, down, left. Up, no. So this would be up, down, left. So it could be any of these. So let's do this. All right, y is 0, x is 0, so is there a down? Yes, there's a down, so it's y plus 1 times width plus x. Wait. Let's just do this. Again, like, so I'm actually debugging this in depending on your interview format, you may or may not be able to do that. Now, if you are able to, then you want to do it, right? You definitely, if you get to the point where you have it written like this, and you have time and you have the tools, you do want to try to debug it. All right, so what is this note? This is, come on. That's bad. Which means I'm probably, so this is x7, y1. Yeah, I'm off by 1 somewhere. Oh yeah, that's the other thing too. You're gonna be off by 1. Right, so it's that. It's that one. So let's, we want to look at these after they've been loaded. Yeah, it's stuck on one. I think I'm populating X7 node. Yeah, darn it. I used reserve instead of resize. See, small problems. But even still, the data doesn't look right, does it? All right, let's take my own advice. What am I missing here? Yeah, so now I'm going on an hour and a half, so I totally have failed. But now I just want to make it work. All right, so I'm looping through the characters and creating a node, setting the color to the integer value of that, and I'm putting that in the list. So there should be 64 in the list. Oh, so much for that. That doesn't seem right. Okay. Color to, all right, now the colors are coming out right. Okay, so for 0, 0, we have a down and a right. Then we have down, left, and right. And that should be true for the entire first row. Yeah, then we go to the second row. There's no left at the beginning. There is an up, a down, and a right. Then we have all 4 until we get to here. There is no right. But there is a left, a down, and an up. We're now on the left again. Right. I mean, it looks okay. So we're on X4, Y2. This is X3, Y2. And if we get to, yeah, up, this is X0, Y2. All right, so now we're on the bottom. There is no down, no left, there is an up, and that should be X0, 6, Y6. Right. That doesn't look right. Yeah, that doesn't look right. Okay, yeah, that would explain that. But left is correct. Yeah, somehow. These should all be initialized to null. Yeah, why? What the heck? Right? That doesn't make any sense. Why is it doing that? Well, X is 7, Y is 1. Oh, wait. There we go. Now we're going 0 through 7, 0 through 7. There we go. Now it's looking much better. And you know what I forgot? So I got all clever with myself. I put the visited flag on the node because we're already there. But then the thing I forgot to do was I forgot to set it. Right? That was it. That was the problem. And because of that, we were blowing the stack. And that's really what was happening. It was just recursing infinitely and it was blowing the stack. Okay, so let's look at our outputs. We have 33 zeros, we have 2 ones, we have 5 twos, we have 6 threes, which I think is about right, if I remember correctly, maybe. So we have 1, 2, 3, 4, 5. No, so it's counting, it's not counting them right. So that's still not right. Twos, we have 5 of them. 1, 2, 3, 4, 5, 6, 7. That should be 7. And threes, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 of those. So why aren't we... So Lori Master is asking about ASTs. Right now I'm working on a symbolic calculator, solves complex maths, expressions, and internally I store expressions as linked lists of nodes. Each node can be a variable constant. Do you think a tree would be better? I mean, there are many different ways of encoding stuff like this. I have always used a tree. Now, I don't strictly use a binary tree. I get the strictest interpretation of like an AST, it would be a binary tree, which would work, but you end up with a lot of nodes. You end up with a lot of unnecessary nodes, in my opinion. So I actually do a composite. I have a node that has a left and a right, and then a list directly underneath it, which I find allows me to encode things fairly easily. For calculators, you can actually encode things. A linked list would be fine, or you could even use a stack, and you could just convert everything into RPN, and that would be the easiest. I mean, like, so in the past, I've built interpreters and languages, and they're simple enough that I can just generate essentially RPN stacks of whatever the expressions are, and then it's just a stack-based thing, and it works beautifully. Fourth is an example of how you can do that. But if you're going to get really complex, you're going to have lots of syntax and nuance, then yeah, I probably would go for a tree. Right, so if you build, like if you follow like an RPN type model, then the innermost expression would be first on the stack. And so those get, you move from the inside out, right? So those would get expressed, and then the results of those would get pushed on the stack. And then as you get to the outermost expressions, then those just consume whatever came prior to it. That, if you can build it that way, and everything works the way you want, and you can express everything the way you want, then I would say go for that approach, because that's a good approach. Now, if you can't express everything that way, or you need more control over the sub-expressions, right, then perhaps a tree makes more sense. But yeah, I mean, there is no right answer. It just all depends on what exactly you're doing. And it sounds like what you're doing would work just fine for what you've got. Hey, Slayer Darth, how'd the interview go? I failed mine this morning. I I was trying to help somebody because they asked me about this problem, and I actually, it's like sort of kind of okay, but like it's really funny that I've now spent 2 hours on it, and I can't. This is why I fail interviews. Because it's just this stuff is really time consuming. Uh-oh. Bad reviews on Glassdoor. That's not good. I gotta take a short break. Grab some more coffee. I'll be right back. I'm back. I'm essentially on $18,000 a year as a full stack developer in London. Wow. Holy cow. Whew. Sure that isn't 18,000 pounds? I mean, 18,000 pounds, I could, yeah, okay. But, ouch. Okay. Wow, that hurts. Yeah. I'm feeling your pain on that one. Okay, I realized what I'm doing wrong here. I think. Okay, so the logic on this is, if I talk myself through this, okay, so the way that this should work is, let's say we're on this cell, this node. He's a 2. So first, we want to recurse anything we haven't already visited. So now we have visited the top, we visited the left, we haven't visited the right yet, and we haven't visited down. So we're going to visit these two because we haven't visited them yet. Now, that's the navigation part. And so that's why I just changed that logic. This, for the count, what we want to do is we want to look at our neighbors. Whether we visited them or not is not relevant. We want to look at them if they exist. And if a neighbor has, is the same color code or same value as we are, then we increment our count in the map. So on this 2, we have 1 2 to the right of us that's the same. So we would increment our count by 1. When we're on this 2, we have this one and that one and that one. So we would increment our count by 3 on this. Then here, so if I'm here, that's 1. If I'm here, that's 3. So that's a total of 4. I'm on this, that's 5. This, 7. Yeah, see, it's going to overcount in that case. That's too much. Yeah, but then the counts are wrong. I know that's not 100% right. No. Burn me heart. What color are you referring to? Okay. That's closer, I think. What do we have? 5 ones. 1, 2, 3, 4, 5. 7 twos. 2, 3, 4, 5, 6, 7, and 10 threes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. All right. That worked. Damn. Okay. Shit. I'm a total failure, guys. This is why I can't find work. So there you go. I suck. Okay. So for a problem that you probably get 40 minutes for, I have taken 2 hours, and it works. So let me talk through what I ended up with. We're getting rated. Jamie Pine Live. Welcome, everybody. So, where do I start? Okay. Welcome to all the raiders. Thank you for the raid. I appreciate it. Hey, Jamie Pine Live. Thank you for the raid. Okay, so what I did was first, really more because I was debugging it than anything. I don't think my original approach was wrong. I think what I had messed up was the visited stuff. So I was getting stack overflows, which I'm going to come back to that because that does have some implications in an interview context. But what I ended up doing was, well, I actually had two errors in the parser. One was this expects a string, not a character, which is really stupid. But anyway, I guess it can be multiple digits, which is why. But anyway, I loop through all the characters in the input, so this string here, and I create a temporary C string so I can get the numeric value, and I create the node here and populate the color and put that in the list. So we populate the whole list with the fully qualified structures, allocated structures. That's done. Then we loop over from a Y and an X perspective, treating it like a grid. We get each entry back out, a reference, we set the X and the Y, and then this logic's fine, right? If Y is greater than 0, then there's an up. If Y is less than the height minus 1, then there's a down. If X is greater than 0, there's a left, and if X is less than the right edge, there's a right. And so all that's fine. So this populates our grid structure, and then from there, I populate the result map, right? So there's 0 through 9 are the possible values. And so I just pre-create the result map with a 0 count. That just makes using it later easier. Then I call walk color node, passing in the very upper left node and the results map. Okay, so here's where, which is what you would expect in an algorithm like this. Here's what I ended up with. So first, if the node that comes in is null, we bail. And also, we don't really need to return the color anymore. Not using that. So the very first thing is we mark the node visited because I'm using the fact that I have these data structures already in place to mark that we've been there. Now it turns out I needed two trackers there. I needed a visited flag for the navigation and I needed a counted flag. So we're going to get into that. So then I get a reference to the count from the map for this color. Then if there's an up, we visit, and we haven't visited that node, we visit it. If our current node has not been counted and the colors match, then, so in other words, if we haven't been counted and the up color matches our color, we increment our count and we mark ourselves as counted. Because once we've counted ourselves, once we've said, hey, we're connected to something, then that's it, we're done, right? We've counted ourselves and we don't need to do that again. Then we do the same thing for right, the same thing for down, the same thing for left. So there's two stages, I guess, or two parts. One is we have to navigate our neighbors. We have to recurse into them, visit them, so that they can in turn visit their neighbors. But also, while we're on the neighbor, we have to determine if we've counted ourselves as being connected in some way. Now, and the way the rules work is it doesn't matter on what side we're connected. If we're connected on a side, we've been counted. So we don't want to overcount, right? So here, this guy's connected both to the left and the right, but we don't need to count that. We just need to, yes, he's connected to something that is the same thing. So therefore, we increment the count. And that is the algorithm recursively. And then we loop through the output result structure and we dump the count for each of them. And that's that problem. Now, there's a couple things, now that I've got that done, and it took me 2 hours to do it, there's a couple things that are going to probably come up. Assuming you get far enough that it's obviously a recursive solution and all that, they're going to ask you some questions, right? So one thing they're going to ask you is, okay, well, what's the downside of recursion, right? Why would recursion be bad here? Well, one is what I just ran into, right? I forgot to do this, and because of that, we were blowing the stack. So that's the issue with recursion, is you have a limited amount of stack space. Now, on most modern operating systems, the stack is actually quite large, but still, you can exhaust it pretty quickly, okay? So how would you do it without a stack, right? How would you do it without recursion? Well, the way you would do it without recursion is we would turn this into a loop. We'd create a stack here. So we'd use a standard stack, right? And we would just push node pointers onto the stack. And so essentially we would take this and make it a body in a loop, right? So it's iterative. Every iteration, so every node, we would do very similar to what we're doing now. Have we visited this? Yes, okay. If we have, go on to the next one. We don't care. If not, right, then the logic would be basically the same, except instead of calling a function, we would push those pointers onto our local stack here. And then and then we check, right, for our counts. So we do all that. Then at the end of the loop, we would loop through the stack, or we'd pop off things to visit, right? And then those would become the next thing in the loop, right? So essentially what you'd have is, you'd have a current node is equal to list 0, right? This is what you would start with. You'd have while true. We'd have a stack here of color node t pointers. Just call it stack. And so what would we do? We would actually, let me move this. And eventually C-line will catch up here. So this is the recursive version. This is the iterative version. So we grab the very first node, just like we're doing with the recursive version. The results we don't have to pass because it's already in frame. Although if we put this in a function, right, we pass it in the same as always. And then what we would do is we would grab that for so instead of node, it would be current node. And this block we just put right here. I'm just going to name this node. There. Now everything matches. If node is, if we have visited, then we need to do stuff here. Okay, so if we haven't visited, we're going to push node up, node down, no, sorry, node right, node down, node left, and then if stack empty break, node is equal to stack top, stack pop. Okay, so what's the difference here? The difference is and I'm going to use an evil goto. Gotos are great. So, what is this thing bitching about? Say what? I'll answer your question in just a second, Savage SKS. Does the compiler feel the same way? It does. Oh, variable. Ah, darn it. Silly, silly, silly. All right. Okay, so node is, we're just keeping track of what node we're on. And we have our stack, right? So what's the difference between this stack and the call stack? The difference is this stack lives on the heap. Well, the call stack lives on the heap too, but it's pre-sized, right? By the operating system, there are limits. And the compiler has used the stack to do a bunch of other stuff, right? So the call stack is not infinite, right? So if you have a machine that has 64 gigs of memory like I do, the call stack is like 8 megabytes, right? And that's what you get. And for most, and you can reconfigure that, but that's not the point. The idea is you want to be able to allocate something and have it grow, right, on the heap and not be a big deal. So this is allocating memory on the heap for us. So theoretically, this implementation of the algorithm can run for as much memory as we have, right? So the iterative approach can have much higher bound than the recursive approach, okay? Now, there are ways that you can do the recursion without running into the stack limit, right? You can play with custom allocators and there's things you can do, but the the simple distinction, and certainly the distinction that they'd be looking for in an interview, is can you take that recursive algorithm and rewrite it so that it's sequential? So this would be at least my initial cut at what this would look like sequentially. So we grab the first node, we have our empty stack, we loop. We grab a reference to the count for the current node's color. If we visited the node, we go to the next node because there's no reason doing more work again, right? We mark the node as visited, and if there's an up and we haven't visited the up, then we push that pointer onto the stack. And then we do our counting, which is the same regardless. Same thing with right, same thing with down, same thing with left. Then we get down here to the bottom of that loop, okay? So then we want to say, well, what do we do next? So we look at the stack. Is it empty? If it's empty, we're done, right? There's nothing left to do. We've exhausted all of our options. So the C++ stack class is a little weird. You can't get the object out of pop. You have to get it from top. There's a reason for that, but anyway, this is a pointer, so we're good. We grab the next pointer off the stack, we pop it because we're going to process it. So then we loop and the process starts. Now node points at some node we want to visit, right? Whatever the next one is. And we keep running that process until we exhaust our stack. And boom, we get the exact same result. See, so these are all the different things that a problem like this, by the way, ended up being 227 C++ lines of code. Some of those are actually unnecessary. Like I ended up with this formatter because I was debugging. That's 21 lines we could take out. So ultimately this ended up being 200 lines of code with a recursive and an iterative solution. So, and so again, the key here is they're going to ask you about the difference between the two. And just so you know, the iterative versus recursive thing, that applies to pretty much all languages, more or less. Perhaps some of the Lisp derivatives, or languages where there are certain kinds of tail call optimizations as part of the just-in-time compiler or the compiler in general, perhaps wouldn't be as applicable. But like Java, certainly Java, C#, JavaScript, there's a limited stack space, so call stack space. So being able to take that recursive function and unfold it into an iterative approach is something that, they're going to want you to do. So anyway, or be able to explain at least, right? So hopefully, my anonymous questioner, this will help you. I feel bad it took me 2 hours and 20 minutes. So I definitely failed the interview. Yeah, no question. But I solved the problem. So I'm pretty happy about that one. So I actually will check this into the question and answer repository, and I'll put links to it for anybody who wants to play with that. And if anybody else has any other questions, problems that you want to see me solve, those are kind of fun. So if anybody else has anything, and you don't have to, I can keep you anonymous. If you want me to mention your name or your handle, I can do that or not. So, but the questions are interesting nonetheless. So Savage